The next section of our chapter on alkanes deal with constitutional isomers. Constitutional isomers are defined as those compounds that have the same molecular formula but different structural formulas. In other words, they're going to be connected differently. Same number of carbons, same number of hydrogens, but the order in which they are connected makes them different compounds. For the molecular formulas, CH4, the simplest of hydrocarbons known as methane, and C2H6, the next hydrocarbon known as ethane, and propane, C3H8. There really is just one arrangement for those possible formulas, so there are no constitutional isomers for those molecular formulas. If you just think about that, and let me just put a slide here and we'll draw those. If this is methane, CH4, and constitutional isomers are defined as different ways to arrange the carbons that are connected to each other, well, there's only one carbon. You can see that there would not be a constitutional isomer. Ethane, C2H6. Two carbons only attached to one another. There's no possible different arrangement to connect the carbons. No constitutional isomer. And propane, three carbons connected to each other. Can you think of a different way to connect those? I mean, no matter how I start connecting those three carbons, I end up really with three in a row. No constitutional isomer. But something interesting begins to happen at the 4-carbon butane. CH3, CH2, CH2, CH3. I now have finally enough carbons to where we can have a straight chain, as in the molecule butane. Now, what if I added 3 carbons, and instead of the 4th one at the end, what if I branched it and placed it on the 2nd carbon? I have now what's defined as a constitutional isomer. Both of these compounds are C4H10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have just rearranged the order in which the carbons are attached. Notice they're all single bonds. The entire chapter is devoted to single bonds, alkanes, but we can begin seeing that we branch the chains. If I consider branching 2 carbons, we really did end up with the same 4-carbon chain right in a row. So really this right here is a constitutional isomer of the straight chain butane. This indeed is not. It represents the same, just kind of branching them in a different order. So with this particular section, we're focusing on something called constitutional isomers. Those compounds that have the same molecular formula, but the different arrangement of those particular molecules. This is the example we drew on the slide. Here's butane, straight chain. Here is the structural formula here now of what we call 2-methylpropane. It's just kind of taking a note here. That might be worth talking about, 2-methylpropane. If I go back and just kind of show what we had drawn here originally, 1, 2, 3 carbons in this chain. And on the 2nd carbon, we have a methyl group. Remember that prefix that represents 1 carbon? Methyl. 2-methylpropane. And we're going to practice nomenclature coming up in a next section, so I'm just kind of seeding that new lesson heading our way. So even though they have the exact same molecular formula, C4H10, they are indeed very different molecules from each other and therefore have their own physical and chemical properties. Let's try some. Do the structural formulas in each set represent the same compound? Are they the same, or are they constitutional isomers? Each compound in letter A has the same structure, C6H14. Both of these compounds are indeed the same molecular formula, but are they different in their arrangement, or are they the same? Let's give ourselves some room and think about that. In that first slide, I'm going to take this CH3, CH2, 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 CH3. See how that's all just connected? We have 1, 2, 3, 4, 5, 6. And if I draw that into a structure, 1, 2, 3, 4, 5, 6. There is its line formula for C6H14. This would be called hexane. Drawing that out, even straight chain, 1, 2, 3, 4, 5, 6. And we come up with this particular model as well. There we go. And if I think about that second choice here, 1, 2, 3, and then straight down 4, 5, 6. 1, 2, 3, down 4, 5, 6. Well, that actually looks a lot like 1, 2, 3, and it came down 4, 5, 6. Are these the same or are they different? Well, in order to be different, they have to have a different arrangement of the straight chain. This actually is the same compound. Do you see that? 6 carbons all linked together. This is 6 carbons all linked together. These are the same molecule. What about that second example from the letter B? If we have 1, 2, 3, 4 carbons in a chain, let's put that on paper. 4 carbons in a chain, 1, 2, 3, 4. And now notice they have at carbon, we'll call this carbon 1, 2, 3, 4. And I'm counting that way because we'll learn shortly that the numbering goes to the longest chain, which actually would be this, 5 carbons, 1, 2, 3, 4, 5. So that's actually a 5 carbon chain, and on 1, 2, 3, 4, 5. The longest chain I can find is 5 carbons. Wouldn't matter if I went up or went down. I'm going to end up with the same numbering system. 5 carbons is the longest chain. And at carbon 2, I have a methyl group. And at carbon 4, I have a methyl group. So let's make clean. 1, 2, 3, 4. And it had a number 5 going down. Also had a carbon up here. And at this particular carbon, we had a second methyl group coming off. And just to finish those structural formulas, we know all the other bonds would be hydrogens. Alrighty. So the longest chain, 1, 2, 3, 4, 5. 5 carbons gives me a root word of pentane, doesn't it? Pentane. And we said if we count at the longest chain, carbon 1, 2, 3, 4, 5. At carbon 2, we have a methyl. And at carbon 4, we have a methyl. And this is not the proper way to name them. We're just kind of getting an orientation here. It was actually called 2,4-dimethylpentane. Again, just seeding a lesson that's coming, but we get an idea that we have 2 carbons hanging off the longest carbon chain. Both of those are just 1 carbons. Now let's go back and examine this structure. Are they the same or are they indeed different? Well, let's first go 1, 2, 3, 4, 5 carbons in a row. So I'm going to draw those 5 carbons in a row. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 carbons. And what else do we notice? 1, 2, 3. At carbon 3, there's a methyl. And at carbon 4, there's a methyl. Put those on. At carbon 3, carbon 4. I just wrote 4, sorry. Now let's consider every other branch here would be hydrogen. What have we made? Longest carbon chain is indeed 5. 1, 2, 3, 4, 5. So we still have a root word here of pentane. However, the methyl group is on carbon 2 and carbon 3. 2, 3 dimethylpentane. These structures are not the same. Structure 1 had the methyl group at carbon 4's position. The second structure had the methyl group at carbon 3 position. These would be constitutional isomers. They are indeed different compounds. Letter A, we determined were the same compound, 6 carbons in a row, but letter B were constitutional isomers simply because they had the methyl groups attached at a different carbon's position along the straight chain. The longest chain there for both was a pentane, a 5-carbon branch. And there's the solution. I recommend pausing the video and make sure you see how indeed these are the same compounds for letter A and they are different compounds for letter B. Let's draw some structural formulas for 5 constitutional isomers for the compound C6H14. There's going to be 5 of them by the time we're done drawing. What are some possible ways we can arrange for C6H14? Well, the first one I think about is just a nice straight chain. 1, 2, 3, 4, 5, 6. Hexane. 6 carbons in a straight chain. If I think about branching, and that's literally what we're going to be having to do next, is trying to find all the different ways we can branch to come up with the different possibilities. Well, 1, 2, 3, 4, 5 carbons leaves me 1 to branch. What if I placed a carbon here at carbon number 2's position? That would be a constitutional isomer. And it would, keep in mind, this would be the same had we gone 1, 2, 3, 4, 5 and just placed the carbon here. That's still going to be a carbon 2 position. So those two are not different. They are indeed the same compound. But, say here's 1, here's a structure 2. What if we went 1, 2, 3, 4, 5, but placed the carbon on this chain? Now I've placed that methyl group on the 3rd position. Wouldn't matter if we numbered left to right or right to left, either direction gives that 3rd carbon that methyl group. So there's a 3rd constitutional isomer. I don't see any other with 5 in the branch, so let's go to carbon 4. 1, 2, 3, 4. I'm trying to just extend the page. Give us a little more room to work. If we have 1, 2, 3, 4, we could place a carbon 5, 6. Now we have at position 2 and 3 a methyl group. 1, 2, 3, 4, 5, 6 carbons. Now, what if we were tempted to consider this structure? 1, 2, 3, 4, and then put those same carbons together. Notice what we really made? The longest chain goes up. That's still a 5-carbon chain, and on the 3rd position, there's a methyl. That is indeed the same as structure number 3. So that's not different. So I had to separate those 2 carbons. All right, so that structure was not different. Let me just get rid of that then, because that ended up to be the same structure. We had to kind of take off each carbon from each other to get another structural isomer. All right, so far, we've managed to come up with 4 structural isomers. What if we go to a 3-carbon chain? I can put 5, 6 on the same carbon, and I can come up with maybe this. 1, 2, 3, 4 carbons is my longest chain. and I placed carbon. Yep, this will work. I found one. So again, I put 3 carbons in a row, but look what happened. My longest carbon chain actually is this one. 1, 2, 3, 4. So now I have butane, still a 4-carbon chain, but now I've put the carbons on the same. So up here in my 4-carbon chain, I put 1 carbon on each, position 2 and position 3. But what if I put them on the same, position number 2? This indeed is a constitutional isomer. This one would be called 2,2-dimethyl butane. Let's see if we can't keep thinking. We need one more. Another way to arrange. 1, 2, 3, 4, 5, 6. Is that different? 1, 2, 3, 4, 5 is my longest chain. And at position 2, we have a methyl group. Nope, we had that one earlier, didn't we? One, two, three, four. I have to get a peek. 1, 2, 3, 4, 5. Oh, you know what? I'm so sorry. There were 5 isomers, and I'm trying to come up with one more and couldn't find it. So we did find our 5, and then I started to keep repeating myself. Some reason in my head I wanted to go 6. No wonder I was struggling. There are only 5 structural isomers. Every time I tried to come up with a new one, I said, well, we already made that, so that makes sense. Sorry for that. We had 5 structural isomers, and here they are. We just drew them in the straight chain. We said 6 carbons in a row called hexane. Then we went to 5 carbons. We said at position 2, we had a methyl, 2-methyl pentane. We put that position in a 3rd carbon of a 5 chain, so this was called 3-methyl pentane. We put them both on position 2 in a 4-carbon chain, 2,2-dimethyl butane, and we separated those out in a butane on position 2 and position 3, dimethyl butane. 1, 2, 3, 4, 5 constitutional isomers, all sharing the same molecular formula, and have just now rearranged the order in which the carbons are linked. That ends the section on constitutional isomers. I really recommend practice just drawing as many practice rounds as you need to get familiar with how can I go about branching the chains to come up with these structural isomers. To do that, here would be a great next step. Just to give yourself a little practice before you start the next lesson. C5H12 is known as pentane in a straight chain. Can you find 3 constitutional isomers for the structure pentane? Pause the video, try it out, and start it back up again when you want to check. Well, let's see if we come up with the same structures. And again, it's just kind of playing with the way that we can arrange them. 1, 2, 3, 4, 5, pentane. Here's one. Straight chain, pentane. 1, 2, 3, 4, 5 would be its structure that direction. All right. What else can we do? What if we went down to 4 carbons in a row? 1, 2, 3, 4 carbons. And I put the 5th one here. Now we have a methyl group on the longest carbon chain. The longest carbon chain there is 4. So we have 2-methyl butane. Thinking about that structurally, 1, 2, 3, 4, and a carbon coming off here. If I had placed it, and keep in mind, I'll just draw this over here. If I had placed the carbon on that particular, I still just number the opposite direction. That's indeed the same compound, 2-methylbutane. It's just flipped. Alrighty, what else can we draw? What about 3 carbons? If I place a carbon here, but I'm going to draw something that we're going to erase. So what if I put it here, and I actually just drew that one above, didn't I? 1, 2, 3, 4 is the longest carbon chain. That's 3-methylbutane. Excuse me, I would number wrong. 1, 2, 3, 4. 2-methylbutane. Putting in the lowest number gives me the same compound we just drew above. So that's not one. But thinking along those same lines again, 3 carbons in a row, what if I split? Now, no matter what direction I place them, the longest carbon chain is indeed just 3. I can go 1, 2, 3, 1, 2, 3, 1, 2, 3. I can't find any longer chain. So what we've created is a propane root word. And off of the carbon, 2,2-dimethylpropane. There are our 3 constitutional isomers for the compound C5H12.